we'll complete the next topic in design and analysis of algorithm, that is a design approach called branch and bound. And in that we'll discuss two problems, assignment problem and traveling salesman problem. So branch and bound is used to find optimal solution, that is maximum or minimum. It is similar to backtracking, that is we search for a solution, but instead of DFS here we use breadth first search or best first search, which is also called least cost search. And here we'll have something called state space tree that will represent all possible solutions, and we'll try to efficiently search this state space. So the first problem that we will look into is job assignment problem. So it's a simple problem where there are n jobs that we have to assign to n persons. Okay, and each assignment will cost some amount. For example, if we assign job 1 to A, it will cost 9. But if we assign job 1 to C, it will cost 5. So like that we have to assign the jobs to the person. Okay. And we have to find the minimum cost assignment. So this is your input for the problem, and the output will be a valid assignment. And when we are assigning the job, there is one constraint. The constraint is one person can be assigned with one job only. So each person will have unique job. So one person cannot do two multiple jobs, or one job cannot be assigned to more than one person. Right? So output can be any kind of assignment, like say job 1 is assigned to A, job 2 is assigned to B, job 3 is assigned to C, job 4 is assigned to D. Now this assignment will have certain cost. For example, if we assign job 1 to A, it will cost 9, job 2 to B, it will cost 4, job 2 to C, it will cost 1, and job 2 to D, it will cost 4. So the total cost for this assignment is 18, right? So this is one assignment. What we have to find is the minimum cost assignment. That is, we have to search which assignment will have the minimum cost, and that is the expected output. Fine. So what is the brute force approach here? So brute force approach means we will try all possible assignments. So how many possible assignments are there? For example, we are trying to assign job 1. We will have 4 options. We can assign to A, or we can assign to B, or C to D. Okay. So 4 options are there. After that, if we try to assign job 2, so if job 1 is already assigned to A, for job 2 we will have 3 options. Either, so A is already booked, so either we can assign to B, C, or D. Next, job 3, same way A and B already booked, so it can be assigned to C or D. Again, if C is assigned job 3, job 4 can be assigned to D. Or here if job 3 is assigned to D, job 4 will be assigned to C. Right? So this represents an assignment that we can see. So every leaf node represents one assignment, valid assignment. Okay. And how much it will cost? So if we see here, job 1A means like earlier we calculated 9 plus 4 plus 1 plus 4. So this will cost 18. While this assignment will cost 9 plus 1. Job 3 is assigned to D. So again 9. And job 4 is assigned to C. So 8. So it will cost 27. So you can see the previous assignment is lesser cost than this one, right? Like that, every path will represent one assignment. We need to search this and find the minimum cost solution, right? And this tree we are calling as state space tree. Fine. So if we apply brute force, how many such assignments are there? So for that we have to find out in this tree how many leaf nodes are there or how many paths are there. So we can easily count that. We can see in this level there are 4 nodes, and each node in next level will have 3 children, and each node in next level will have 2 children, and each node in the next level will have 1 children. So total number of assignments are 4 into 3 into 2 into 1. So that is 24. So if we want to find the solution, we need to evaluate all these 24 assignments, and from that we have to find the minimum, right? And in case of if we have n person and n jobs, in that case number of assignment, I hope you can understand, will be n factorial. So time complexity is order of n factorial, which is exponential, right? So let us see, can we do better using branch and bound, better than brute force? Okay. To apply branch and bound, we will be using 2 costs. One we will call as lower bound cost, another one we will call as upper bound cost. So what is lower bound cost? This will indicate that the solution will at least cost this much, at least or more. So solution will cost at least or more. Okay. So this will give us some idea that if certain solution cannot go below this. So how can we estimate that? Let us see. So for example, if we look at every row, or every column. Let's look at first every column. Job 1. So job 1 will cost at least 5. It cannot be done in less than that. Similarly, job 2 will cost at least 4. Job 3 will cost at least 1. Job 4 will cost at least 4. Okay. So here the cost will be 5 plus 4 plus 1 plus 4. So the solution will cost at least 12 or more. Same way we can look at it row wise also. So if we are trying to assign a job to A will cost at least 2, B will cost at least 3, C will cost at least 1, D will cost at least 4, right? So here row wise if we take, the cost is 2 plus 3 plus 1 plus 4, that is 10. So either we can take column minimums or we can take row minimum, and that will give us we don't need to take both here, either one we need to take, and that will cost, that will give us the lower bound. And please note that this may not be a valid assignment, it just tells us that solution cannot cost less than this. For example, here what we have assigned? We have assigned job 1 So we have assigned A with job 2, B with job 3, C with job 3, D with job 4. So you can see there is a conflict. B and C both are assigned same job. So this is not a valid assignment, but it gives us the lower bound, and we will be using this lower bound to guide our search. And then we will be using another bound called upper bound, which will tell the best cost solution found so far. So we will be searching the tree, and anytime we find a solution that is costing lesser than previous solution, we will be updating this upper bound. So we will improve our search using these two bounds, lower bound and upper bound. So let us solve this problem. We'll expand the node with the least cost. So we'll be using the lower bound to select the next node, and we'll prune the higher cost node. We'll use the upper bound to prune or cut off some searches. We'll look at it with the example, and we'll maintain a set of live and dead nodes or open and closed nodes. So let us solve the problem that we have taken earlier. So on the right hand side I have given the matrix, left hand side we have given the search tree. So we'll start with the start node. At the beginning, what is the lower bound? So we'll take row wise here instead of column wise, right? So the first row minimum is 2, second row minimum is 3, third row minimum is 1, fourth row minimum is 4. So lower bound is 2 plus 3 plus 1 plus 4, 10. Okay. Now we have only one node, so next we will pick up this node only, and we will generate all the children. What are the children? All the possibilities. What possibilities here? We are trying to assign the person with different jobs, right? So we'll start with person A. So person A, we have 4 options. He can be assigned job 1, job 2, job 3 or job 4, and each of those will create a node. Now if person A is assigned with job 1, what will be the lower bound? So if person A assigned with job 1 means this is fixed, right? In the solution already this is considered. Now B, C, D cannot be assigned job 1. They can either take job 2, job 3 or job 4. Which one we don't know. So for the remaining 3 we'll take the minimum, that it will cost minimum this. So we'll leave the first column or job 1 column. B next minimum is 3, C minimum is 1, D minimum is 4. So total it will cost 9 plus 3, 12, 13, 17. So the first node lower bound is 17, right? Same way second node is person A is assigned with job 2. Person A job 2 means this is fixed, so that will cost 2. So B cannot be assigned job 2. B can take job 1, job 3 or job 4. Minimum it will cost 3. C can be assigned again job 1, job 3, job 4. Minimum will cost 1. D can be assigned job 1, job 3, job 4. Minimum is 4. So this will make the lower bound 10. Okay. Next, if A is assigned with job 3, then this is fixed. It will cost 7 plus B minimum of 6, 4 and 7 is 4. C, minimum of 5, 8 and 8. We cannot take 1 because job 3 is already assigned. So out of this minimum is 5. D, 7, 6, 4. Minimum is 4. So total will be 20. Right. So next node minimum is 20. And third option, A is assigned job 4. So it will cost 8. And then we can take the minimum here, that is 3 plus 1 plus 6. Total will be 18. So right now this node will be dead or closed, and we have 4 allied nodes. So closed nodes or dead nodes means the children are already generated. Live nodes means for these nodes children are still not generated. Okay. So next, which node will pick up? So if it was DFS, we will blindly pick up the first node. Right. So instead of that, here we will be using best first search or least cost search. So which node is costing least or having the least lower bound? So that is the second node, this node. So we'll pick up this node next and then generate its children. Okay. Other nodes, like first one is lower bound is 17, second one lower bound is 10, third one lower bound is 20, fourth one lower bound is 18. So 10 is minimum, so we'll pick up this node. Fine. So from this node, how many children we can generate? So already A is assigned in the first level. Second level is representing B. So A is assigned with job 2. So B, how many options it will have? B can be assigned with job 1 or job 3 or job 4. Right. So for each of these nodes, new nodes, we will again calculate the lower bound. Okay. And so let's calculate for this node lower bound. So A is already assigned with job 2, means it will cost 2. B is already assigned with job 1, that means it will cost 6. So C cannot be assigned job 1 or job 2, either job 3 or job 4 it will be assigned. So minimum is 1. Same way for D, minimum of these two is 4. So that will be total 6 plus 2, 8 plus 9, 13. So lower bound for this node is 13. Next we will pick up this node. What is the lower bound for that node? This node means A assigned job 2, B assigned job 3. So C is left with job 1 and job 4. For that minimum is 5. And D is also left with job 1 and job 4. Minimum is 4. So total lower bound is 2 plus 3 plus 5 plus 4, 14. Okay. Next we'll pick up this node. Here what is the assignment? A is assigned with job 2, B is assigned with job 4. So for C we have the option either job 1 or job 3. Minimum is 1. For D also job 1, job 3. Minimum is 7. So if we add that, I think there is some mistake here. It will be 2 plus 7 plus 1 plus 6. Okay. So that is 16. Not say 6, 7, sorry. 17. Anyway, does not matter. Fine. Now this node will be closed. So what are the open nodes we have? So right now we have, these are the open nodes, right? And you have to pick the minimum among them. So what kind of data structure we can use for this? We can use priority queue or heap, right? Min heap. Fine. So out of these live nodes, which one is minimum? So obviously we have 17, 13, 14, 16, 20 and 18. Minimum is 13. So next we will pick up this node, right? So from this node, how many children we can generate? So this node means A is already assigned, B is already assigned. Next level represents C. C, A is assigned with job 2, B is assigned with job 1. So C has two options, either job 3, job 4, right? So we'll do that, C job 3, C job 4. And if C is assigned with job 3, D will be left with job 4. And if C is assigned with job 4, D will be left with job 3, right? So you can see what is the assignment cost. So A job 2, B job 1, C job 3 means cost is 1, and D job 4. So total cost is 6 plus 2 plus 6, 8 plus 9 plus 4, 13, right? And this is a leaf node because below this there will be no other assignment. All persons are already assigned with job. So we'll now update the upper bound. So initially we'll set the upper bound to infinite, and if we found a solution whose cost is lesser than the upper bound, we'll update it to that. So the upper bound will be updated to 13. This is wrong, don't look here. Fine. Next we'll go to this one. What is the lower bound here? So here also job 1, A is assigned with job 2, B is assigned with job 1, C will be assigned job 4, D will assign job 3. So total cost 2 plus 6 plus 8 plus 9. So that is 25, right? Fine. Now this is a leaf node, yes. The cost, is it less than the previous cost? What is the previous cost? Our best solution found so far is 13. This node cost is 25. So we don't need to update it because this solution costing more than the solution already found. Okay. Now this node will complete. We'll pick up the next node. What is the next minimum node? So these two are completed. Next live nodes are 17, 14, 16, 20, 18. In that minimum is 14. So it is telling that if we go down this path, the solution will cost at least 14 or more. But so far already we have found a solution cost 13. So do we need to go down this path? No. Because already we have a lesser cost solution. So here we will do something called pruning or bounding. So we will be bounding here. So this way we will stop generating unnecessary node, which will reduce the search space or searching cost. Same way, if we pick up the next node, what is the next smaller node is 17, which is again larger than upper bound. So we will prune that node. Next is 16, okay, 16 or 17, whichever, these are larger than. So next all remaining nodes are. So we can see that remaining all the nodes cost is greater than upper bound. So all remaining nodes will be pruned and the search will stop, and we have found a solution. The solution cost is 13 And what is the assignment we got? We assigned A with job 1, B with A with job 2, B with job 1, C with job 3, and D with job 4. And this is the least cost solution or minimum cost solution. So this way, in branch and bound, you will be using the lower bound to select the nodes, and you will be using the upper bound to bound or prune the nodes which are costing more than the solution already found. Fine. So this is our optimal solution or optimal assignment, and this is the total cost.